Okay, I'm assuming we're all here. So my name is Todd Swanson. I'm going to be the moderator for the session, but you won't hear much of me. I'm going to pass it over to the presenters today, and they're going to introduce themselves. But we have Laura, Robyn, and Ryan. I think the talk of the title, or the title of the talk is fascinating to me. Broadening the Path of Totality, sharing the 2024 total solar eclipse as a live experience. It's going to be fascinating to listen to. I'm glad you're all here. And I'll let the presenters introduce themselves and kick it off. Thanks, y'all.
All right, thank you so much. My name is Laura Peticolas, and I work at Sonoma State University, up the road about 4 hours, 3 if traffic's good. And I'm here to tell you a little bit about a project I'm leading called the Eclipse Mega Movie. So on April 8th, there will be a total solar eclipse, and the moon will completely cover the sun, the photosphere of the sun. And then for those of you who might be going to Texas or New York or Indiana, you would see that phenomena, and then the corona, or the atmosphere of the sun, appears, and the stars appear, and it gets cold and dark. And on the right, you can see this photograph that one of our volunteers in 2017 took during the total solar eclipse. And we were doing this in 2017 as scientists. I worked at UC Berkeley at the time. And we were working to try to get, for 2 goals. One is just to get people to go to the place where you could see this solar corona and experience this amazing phenomena called the total solar eclipse. Did I lose it? And so then, and the other goal was for science. So basically the place where you could see this phenomena was over a big swath of the United States, from Oregon all the way to all the way through Nebraska and down through the Carolinas. So we had photographers that set up across that entire path, and we had 50,000 images uploaded afterwards, and we created a movie out of it. And it's not like a movie with a plot, but it's just a video of the sun's atmosphere. And over time, it changes very slowly, which is very exciting to those of us who study physics. So we're doing it again, but this time we got funding from NASA because we proved we could do it. And we're asking people to take photographs with very nice cameras with big lenses, 300 millimeters or up to 600 millimeter lenses, and DSLR. If you know what that is, you might have one of those cameras, both mirrorless or mirror. They're digital cameras that can capture this phenomena. And we're also asking that that our volunteers hook up to a computer so that they can enjoy the experience for the 6 minutes, or the 4 minutes, only 4 minutes this time. So that's part of what we're doing. But I think even more interesting to you all at this conference is that we are also going to then engage people in machine learning using the photographs through a Kaggle competition. And part of that, we have students right now at Sonoma State University who are working with a professor there in machine learning of images, and they are creating what's called a data set, training data set from the 2017 data. And then we'll use that in the upcoming 2024 data set. So we're still going to be looking for volunteers. If any of the students you work with or the public you work with is interested in that, we'll be putting a call out for some of those competitions. Okay, so this is that was kind of my whole pitch. So I'm going to just quickly go through some of these other slides. So here's what I was talking about. This path, the shadow of the moon basically crosses the US. You might have seen the partial in October. That was kind of cool. Shadows, all the cool shadows that happened. So that will happen again everywhere here in California. And then this is kind of what the partials of the eclipse look like. Up at the top These are photographs of a total solar eclipse, and you can see partial solar eclipse. You see the photosphere, see some clouds in these pictures as well. And then you have this kind of what we call the diamond ring. So on the moon, there are craters, as probably most of you know, and then the sun can peek through those craters and create this bright light. And so that's why it kind of looks like a diamond ring when you take a picture of it. This is that shadow play that I was telling you about. This was at my house, actually, up in the North Bay. And you can see that that's not the moon. That is the sun being blocked by the moon. But it looks a lot like the moon at night. And you can make all these little pictures of the sun using holes. It makes this pinhole camera. So here's a picture of the 2017 eclipse. I was in Wyoming, and we are up on this hill, and you can see at 11:28 a.m. it was darker than it would have been normally because it was a partial eclipse. But then when you're in totality, it becomes dark. And like I said, you can see the stars. You have these silhouettes of people because it's dark and cold. And that only happens for 2 minutes. So here's some of the people who signed up to take photographs. So sometimes they were families and couples and single folks. Here's some more. I just love these photos because there are true heroes of the project. I really love this graphic. Pat Rife from Rice University in Texas posted this recently, and it reminds us that whenever you're in the partial phase of a solar eclipse, you need eclipse glasses. And you can look at the sun at any time with eclipse glasses. They're really solar viewers. So if you have solar viewers and solar eclipse glasses, you can go out today and look at the sun safely. It will just be a circle. But still kind of cool. But then if you happen to go to this path of totality to see the corona, you have to take the glasses off. Some people keep the glasses on. Oh, look, Robyn has some. Great. And then you won't see it because it's about as bright as the moon. And so if you try to look at the moon with these solar viewers, you won't see the moon either. You don't have to believe me either. You can try it yourselves. Okay. So this is when we processed some of the data. This is what it looks like. So we take multiple exposures and then, our volunteers do, and then we stitch them together. We do this complex algorithm to match all the circles together. And then you can see all these really cool features in the atmosphere of the sun. And then we had some students working with us, and my colleague from UC Berkeley and I mentored a student at Sonoma State. Well, she was an intern at Sonoma State, but she's actually at Dartmouth. So there's just a lot of interactions between students at different universities, which has been really fun for this project as well. And you can see on the left was our high dynamic range image. So with all these exposures together, and then we subtracted those from two different places under the path of totality. And that shows some of what's going to be changing in the corona. So that's our analysis. That's how we did some of the analysis. And some of our colleagues from Japan had done this as well. And you can see there, they found these things called plasma jets. And those are the things that we're going to be studying for this eclipse. So I won't go into the science of plasma jets. You can ask me about that later if you want. But again, if you're interested in being part of either the eclipse photography or the machine learning, for the photography, you really do have to be under this path of totality. So you can't be here in California. But you can do the machine learning from anywhere. So you can sign up for that. We'll get that started in another month or so. Okay, so now I'm going to pass it on to Robyn.
I have my own.
Oh, you have your own. Great.
Before I start, are there any questions? So this is a citizen science project being led up. So if people are interested, there's a QR code there. You can take a picture of it with your phone and participate. It's great, right? You're having great results and all of that. So anyway, one way to participate, there's several citizen science projects going on, most of them being funded by NASA. So if you're interested, again, it's 2 weeks from today. So it's time to start looking. There's a one about soundscapes. There's one that's going to track cloud cover in the sky on the day of the eclipse, temperature readings. So if you're interested, we can talk more about that later. Okay, is there another slide? Oh, you have it. Oh, cool. Okay, so this is me. I'm Robyn Higdon. I'm so excited to be here. And I've been working with NASA to do live streams of the eclipse for about 25 years now. And Scenic actually has been putting up links to this for almost as long. And so being here in California, I know I'm from the Exploratorium. We're in San Francisco. We're only getting a partial eclipse this time, just like in 2017. We only had a partial eclipse also. But what we do is I go with the team from the Exploratorium and we go into the path of totality. In this case, we're going to be in 2 locations because the weather in April is pretty dicey. So I have 2 locations for this one. I'll be doing live streams. So I can talk about those in just a minute. I know this is a lot of text, but we're doing 4 different streams, right? So the idea is to support you, as best we can. So what I'm going to do is I'm going to have a team in Mexico, high desert, good weather. So I'm going to be broadcasting 3 hours, the entire eclipse. And it'll be available to you. And it's just images from our telescopes. So it'll just be telescope images. So if you want to do something in class, if you want to show it in the lunchroom, if you want to talk about it with that in the background, like this is a good feed for you. At the same time, I'll be doing a similar broadcast, just telescope feeds from Texas. And, you could put up both feeds and watch because totality is going to happen in Mexico first. Totality in Mexico will be ending about 10 minutes before totality starts in Texas. So there's lots you could talk about there, about the shadow moving along the path. You could sort of compare, where each of them are in their totality from these 2 locations. And then if you're like, I just want to sit down and have a coffee that day. We're doing a 1-hour show, just like a TV show, Exploratorium educators, NASA scientists. We've got some youth doing different things. They're very excited. So they'll be doing a 1-hour show in English. And then, of course, because we want to expand our audience as best we can and serve people in California, we'll be doing a 1-hour show completely in Spanish with native Spanish speakers. So again, 1-hour TV show is the best way to explain it. In our sort of educational programs, you'll get to see both totalities. So they'll be referring to the telescope images a lot, and they'll show totality first in Mexico, and then 10 hours later, you can watch totality again. So should be fun. They're there. If everything goes well, technically, live TV be a little dicey. The archives of these should be up within a minute or 2. If we're having technical difficulties, sometimes it takes 24 hours. So you'll know how many gray hairs I have by when the archive goes up. But again, if you want to be out, doing great pinhole things outdoors with your students that day, and instead check in with these broadcasts the next day, they'll be available for you. So here's how you can get to them. Exploratorium, hopefully you guys have heard of us. It'll be on our website, exploratorium.edu/eclipse. So you can go watch them there. You can make them full screen. We also have an app. So if you are outside and you're doing fun pinhole things, you can actually watch the telescope views. And the telescopes are close up. So you see details on the sun. You can see, prominences on the edge of the sun close up. Because when you put these on, and you look at the sun, the sun is like that big in the sky. But having both is a really nice experience, doing both. The timing's going to be off, remember, right? So you'll be seeing totality there. It'll be partial here. Timing's a little off. Or you can go to our YouTube channel. I don't know if you do embedding, but a lot of people like to embed our stream somewhere else. So just go to YouTube. You can grab it there. No problem. All 4 streams. So they're available in all those different ways. And by the way, if there's some way you would want it, I probably can't do it this time, that I'm not delivering to you, you should let me know. And Scenic says they're going to put links on their front page, starting like the day before or something. So if you can't remember Exploratorium, you can go to Scenic. Here's again, I just threw up some ideas here. At the Exploratorium, we just sort of put them up in all the galleries. So even if people aren't like watching the eclipse right there, it's like background, you could put them up in your lunchroom if that happens. Maximum totality in San Francisco, which is probably close to where you are if you're in California, is at 11:13. That's when the moon is covering the most amount of the sun in California. Okay, yeah, I mentioned the app outdoors or just watching the program. And then I just wanted to mention a few other resources that we have on our website if you're looking for them. We do have some hands-on activities on our website that we aligned with the NGSS standards. And they're a little complicated, but hopefully the Exploratorium. There are things to do with paper cups and little balls and, everyday objects, nothing too expensive. So you can go there if you want to do, a real physics lessons that day. There's some ideas for you. On our website, of course, we have all kinds of videos and information, safe viewing things, little factoid videos and all that. So cruise around, it's all there for you to use, whatever you want. There's a lot of information on building safe viewers. Laura was talking about, really, a colander is the best. A drainer, like for spaghetti, anything with little holes. I like to make them too. Like we usually get a square hole punch because the kids are like, that's amazing. It's a square hole, but it'll make a round image before the eclipse and then a crescent during the eclipse. It's also really fun to take those things outside the day before, right? And you're like, hey kids, look at this colander. And they're like, what? It's round. And you say, no, it's an image of the sun, and they don't believe you. And then the next day you get it out and go, look, kids, it's a crescent because there's an eclipse. And that's pretty cool. And then also last October, there was an annular eclipse, which is a very special kind of partial eclipse. And we partnered with the Navajo Nation. We broadcast it from Bears Ears National Park in southern Utah. And so there's some really great videos that people love with some of our Navajo friends talking about the eclipse and what it means in their culture. So they have a very different way of experiencing it out of respect for the sun and moon, out of the understanding of what a important and rare occurrence it is. Traditional Navajo go indoors and they experience it indoors by not looking at it directly. So we have some videotapes that sort of talk about that and about their understanding of the cosmic relationship between the sun, earth, and moon. It's really nice to bring the cultural things in. And the kids really like that too, just a different perspective than ours. And I think that's it. And by the way, there's going to be lots of questions at the end. If you have any questions for us, we have lots of time. And I do have some eclipse glasses because I always have eclipse glasses. So if you want them, I reiterate what Laura said. I used to stand out in front of the Exploratorium non-eclipse days and just hand these to people to look at the sun. And people are like, I can look at the sun, and they put them on and they're like, wow, it just feels cool for a minute. So if you've never done it, afterwards, come up here and get these and go outside and look at the sun. And feel free, I don't have a ton, but feel free to take some back to your classroom if you want. Okay, I'm going to turn it over to Ryan.
All right, very good. Thank you. So my name is Ryan Wyatt. I don't have a slide with my name on it, so I'm afraid you're going to have to just remember my name. I'm at the California Academy of Sciences, as I called it before, the other great science museum in San Francisco. And I'm going to give you a little bit of a different perspective. This is how we've been talking about the eclipse in some of our immersive venues, the planetarium and in other spaces at the Academy. And so I'm going to use some software that's actually open source software called OpenSpace. It's developed, it's funded by NASA and is developed by a consortium of universities. And so this is free to download, a little bit tricky to show some of the data sets that I'll be showing, but a lot of this is quite readily available. And I'm actually starting with a very different perspective because what you're seeing here is kind of like the beginning of 2001 or something, but it's also just an image of Earth in the foreground with the moon and the sun in the distance. And even though the moon is a lot smaller than the sun, it's a lot closer. So that little moon disk is roughly the same size as that little orange disk, which represents the sun, and the kind of big white kind of circle around that is just a way that we show that the sun is bright in the planetarium because we can't make it as bright as it really is. So this is kind of a cartoon view of the sun, but we're going to see some more data-oriented stuff here in a moment, because what we want to tell people about is like what the physical relationship between these objects is that causes the event that we'll be seeing on April 8th. So I'm actually going to kind of approach Earth here and actually kind of begin to zoom around. So the moon and the sun are going to disappear off to the side there. But I can actually take you in a little bit closer to Earth, and you can see, and here I've I've artfully removed the clouds and everything from Earth because we can do that in planetariums.
Yeah, I was just
And
going to say.
sadly, we cannot do that the day of the actual eclipse. But you can see the moon's shadow on Earth. And actually what we can do, again, in planetariums, but not in real life, is we can actually speed up time. So I've actually made 2 minutes passing by every second. And you can see the shadow as it creeps across. And kind of like you were saying, it's going to be a 10-minute time difference between Mexico and Texas. But here we're seeing it move across the Midwest and into the Northeast. And actually then we can also put down the path. So you can kind of see that blue center line represents where totality can be observed on Earth. And so we talk a little bit about what you can see and why we see it, the relationship between Earth, the sun, and the moon. And I could go into details about why it doesn't happen every month, but so on and so forth. So we talk about that physical relationship, but then we also want to give an indication of why we'd want to study this, because you've already seen these beautiful images of the solar corona. So the images from the 2017 eclipse and the ones that are being teased apart by machine learning to understand how the kind of stuff flowing off of the sun's surface is changing over time, because this is the beginning of a relationship between the sun and Earth that is deeply interesting to those of us who actually use any devices that require GPS or make use of satellite data, because this interaction between the sun and Earth is what we sometimes call space weather and the impacts that it can have on Earth. So actually, I'm going to show you a data set here that is the relationship in some sense between Earth and the sun. It's a lot fainter than I expected it to be, but hopefully, actually, let me start the time moving here. Let's see. And you might be able to see okay, that's vastly fainter than I expected. But anyway, these are blue kind of representations of Earth's magnetic field. Really easy to see on my screen, so maybe I'll just have to show people one-on-one when I can show it to you on my much clearer monitor. But that sort of faint diaphanous blue kind of clusters of lines that kind of move in along Earth's magnetic field. Like if you played with a bar magnet as a child, you have a good sense of what this kind of looks like. Although, and you can kind of tell this, you'll see that you can see Earth, the sunlit side of Earth. So you can imagine that the sun is off to the lower right here in this image, that the magnetic field is actually compressed along that axis. So in the sunward direction, the sun's solar wind is actually interacting with our magnetic field, compressing it, and then the magnetic field extends in the anti-sunward direction, away from the sun, at a much longer, and it's actually stretching off the screen on the left. So that didn't show up as well as I would have liked, but basically that's a way of introducing the Earth's magnetic field. And because it looks a lot like that sort of experience that you might have with a bar magnet, and actually some of our demonstrations, we bring out a bar magnet and let people play with magnetic filings and kind of think about a magnetic field. But if we go to the sun and start talking about its magnetic field, then things get more complicated. Now, I should note, and this one I'm convinced you will be able to see much more clearly, this kind of set of little spindly hairs coming off of the sun's surface here. What we're seeing is the sun color-coded, red and blue. I forget which one's which, like the north and south poles of your bar magnet or of Earth. And basically, if you zoom in close, you can actually see that it's not a simple bar magnet. These magnetic fields are tangled and twisted. And because the sun doesn't have a solid surface, that changing sort of morphology of the sun causes a changing magnetic field. And there are little faint dots flowing along these magnetic field lines. You probably can't see there on the screen, but those kind of represent the flow of material along the magnetic fields. And basically what's happening is that the sun goes through periods of activity and relative inactivity. We're reaching a point of sort of solar maximum right now, when the magnetic field lines, and actually if you look on the upper left there, you'll see lots of a much more complicated collection of blue and red blobs. That's because the magnetic structure there is more complex. And regions like that can actually erupt, essentially, and the magnetic field lines with plasma entrained with them can create these events, or in a more quiescent sun or as a quieter sun. We see kind of that gentle corona that we saw in 2017. But since the sun is currently reaching a period of solar maximum, we can expect that we might see some more exciting stuff going on. So for example, here, we're going to shift to another representation of the sun here, the sun as it sort of appears in near ultraviolet wavelengths. And here, a model that's created by NASA's Goddard Space Flight Center of one of these eruptions occurring from the sun's surface. Now, I can only imagine what a solar eclipse might look like if one of these events were taking place when we happen to have the Earth, Moon, and Sun aligned. But here we're just showing a data set, which in our programs we explain in sort of greater detail, of the material flowing away from the sun about 1 million miles an hour. And this is sort of the punchline of why we study these events and study the sun's corona, because it helps us understand how this relationship starts from the solar corona to the solar wind to these kind of events that can impact Earth. Because to add you something a little bit of scale here, I just put up the orbits of the planets. So you can see the innermost planet Mercury, then Venus, Earth, and Mars, the 4 orbits that are relatively close to the sun. You can see that this material over the course, again, we're speeding up time, but over the course of a few days can traverse the distance between the sun and Earth and potentially impact those aforementioned GPS satellites and other electronics that we depend on in our modern world. So this is kind of again, free software called OpenSpace, which is funded by NASA and developed by a consortium of universities that we use at the Academy of Sciences to talk a little bit about these kind of events and other celestial events with our audiences, and sort of a different perspective on the sun, space weather, and our upcoming solar eclipse.
Okay, there's so many things I want to comment on. So solar maximum, just like a week ago, there was one of these giant solar events, and it actually took out, I want to say, ham radio. Went a little on the fritz for a while there. So what's happening on the sun actually affects us, right? It's not just like, oh, that happens. There's a famous event, the Carrington event. When was that? 1896, I want to say. There's a giant solar flare, and it actually caused the whole East Coast to black out. So these things have really. So they also cause auroras. So that's the good side. The beautiful auroras that you see are caused by this activity on the sun interacting with our magnetic field. In fact, they were talking about aurora being in Northern California. Was it today, yesterday? Because of a big solar flare. So these things really do have a connection. There's a connection between the sun and Earth that we like to talk about a lot. I'll also say just another factoid, because it's solar maximum, there's an 11-year cycle. So the sun is super active, which also means during the eclipse, if you look at some close-up images of the sun, there should be lots of these beautiful flares and eruptions on the sun, that it also means the corona is going to look different. This will be my 7th total solar eclipse. And usually I see lines going out sort of around the equator, or maybe one big sort of, bit of light going up like this. Because it's solar maximum and there's so much happening on the sun, it's going to be very star-like. So it should be a beautiful corona. They've done predictions, of light sort of coming out all the way around the sun. So as far as eclipses go, this should be a beauty. So again, something to look forward to. Sorry, I jumped right in.
Oh, no, that was perfect timing.
Okay.
Because I think that is one of the things that you can see in this. So this is a computational model of an event that took place in actually back in 2000. So this isn't just artwork. This is a computational model of that event based on observations from different spacecraft, both from a distance, and also observations made in situ of the magnetic field in different locations in the solar system. And that, to your point, the kind of dominant structure that we tend to see is along sort of the plane of the solar system, but these events and during a solar period of solar maximum can be above and below the plane of the solar system in really exciting ways.
And that coronal mass ejection, that's actual plasma. It's like bits of the sun. It's actually matter being shot out into space. Luckily, again, a lot of times they shoot away from us, and not straight towards Earth. But NASA's spending a lot of time right now trying to do predictions on this, which is called space weather, because again, it can really damage our spacecraft. It can be very damaging to astronauts who are in space. Our big ambitions to go to the moon and Mars. It's going to be important to understand this. And an airline? Yeah.
I'll just add, just in terms of some of the impacts on society, there's some of those particles are going near the speed of light. When they come to Earth, even airplanes flying over the poles become very it's damaging to the people who are in the airplanes. It's damaging, and there's too much radiation, in fact. So there's a whole network between NASA, NOAA, and there's another organization, and they work together in order to basically tell pilots that you need to move out of, like, if there's a polar flight going like from Frankfurt to San Francisco, then they'll actually have to reroute that airplane when these events happen. So, and a lot of the stewards and stewardesses have to wear radiation patches when they're flying over the pole for this reason. So there's, and because of this, it's actually, there's a lot of agencies working together on this space weather initiative that frankly the public knows very little about, which is fine. But to keep us safe, and GPS gets knocked out. You might have noticed, I've been noticing, we've had such a quiet sun. GPS has worked so well, but 10 years ago when we were driving around, GPS were fairly new, you'd be like, where is this taking me? And that's starting to happen again. And I've been wondering, it's very likely due to these solar connections. So just the error bars on the GPS location, it gets bigger during solar activity. So.
Okay, questions. Eclipse things, solar things. Is everybody ready? Are your schools open? They're open on Monday, right? In Texas, I'm going to Texas, and they've closed a lot of schools. It's spring break. Oh, right. It's spring break in San Francisco, too. That's right. Yeah.
That the governors have the state of emergencies that have been declared in Travis County, around Austin and Ohio, because 1 million people are going to try to come to those locations to see it, which, if you think about trying to get there in a plane and deal with the world's greatest traffic jam in, memory, looking at the streams from your exploratorium and other places might be an alternate thing to think about. This is giant. I mean, this is about the biggest internal movement of people at one moment for one day that we've probably ever seen.
It is, and I'm always torn. I start going out usually about 2 years before and talking to people, and yeah, traffic jams are a problem. That said, experiencing a total solar eclipse, I know you're not going to be in school, so you could drive. I don't know if you saw the one in 2017, but it's amazing. Yeah. Mm-hmm. Yeah.
So at the California Academy of Sciences, we are a research institution of the life sciences. So we actually had in 2017 a program called Life Responds, which was looking at, so it's interesting because there's tons of anecdotal evidence about this. It's always talked about, but there are very, very few systematic studies. And so 2017 Life Responds was one of the first systematic like citizen science, community science projects. We had some interesting results, which I really should know more about because I should be prepared to talk about it. But we're doing it on a smaller scale for this event as well. And it's all through the iNaturalist app. So and honestly, even if you're just near sort of totality, the lighting changes can create measurable effects. So it's an interesting project. And also it's something that we've alerted people if you've got bad weather, you may still have lighting changes that would cause reactions to the part of life. So something that you can do even if you get clouded out.
Yeah. So just to reiterate this, so oftentimes during totality, animals will go into their evening behaviors. First one I saw in Turkey, I was in an ancient amphitheater. I had no idea. And all the bats came out during totality and they started swirling around and chasing bugs. Crickets will start chirping. You're right. So the animals, oh, it's nighttime, and they'll start doing their nighttime thing. So it's fascinating. iNaturalist is a great place. If you want to have your students, or if you're interested in citizen science, there's also another one called the Soundscapes Project. It's a national citizen science project where they're going to try to be recording animal behaviors during the eclipse. It's amazing.
So, Jeff Weekly, UC Santa Cruz. I'm flying to Austin to see the totality. And I got an email or a text message from my friend who is hosting me. And she said, hey, I was wondering, are we planning on driving anywhere to go see it? Because the traffic is going to be really bad, they said. And my response was, how is the traffic in your backyard? Because I looked at the maps and I thought, well, it's supposed to go over Austin, not directly over. So my question is, what's the difference from being right in the center of the line to be sort of like 2/3 out on the edge?
Great question. And the answer is time. So in Austin, I think you're going to get about a minute of totality, maybe 120, something in that
something
range.
like 120, 130 is what I saw.
As you drive west from Austin, if you drive west about an hour, half an hour to an hour, you'll be getting over 4 minutes of totality.
So 60 miles, because I don't think it's going to be an hour drive.
Right.
Right.
60 miles. Yeah.
You know what, to be honest with you, and do what you will, it's going to be great in Austin. I would get up at 3 a.m. and I would drive till I got closer to the center line and just pull off at a gas station or in a field. Don't go to Fredericksburg. It's going to be a nightmare. Don't go to Kerrville. Kerrville's a big NASA sunspot, so it's going to be totally overwhelmed. Fredericksburg's always busy. So this is the cities in the hill country.
Right.
But I would drive west because it's amazing. So really, even an extra 30 seconds or a minute might be worth getting up. That said, none of us really know how bad the traffic's going to be, and it will be bad. In Casper in 2017, I was in Casper, Wyoming, and people were driving up from Denver. And people drove up and got stuck in traffic and just got out of their cars on the freeway to experience totality, which is sort of okay, but you should be ready. And it's sort of like what you're up for. But every minute counts. It is just, I don't know if you've seen one before, but it is
No, never a totality. No.
it's
Maybe
incredible.
we'll ride bikes to sort of the edge of town, and find a park on the edge and do it there.
Yeah, every bit that you move west, it'll get longer.
I'm not kidding.
Don't get in a car then if you don't want to. Okay.
About 5 more minutes. So just to make sure.
I'm going to be putting Northwest Arkansas. I'll be in that area. I've done a lot less traffic when
Yeah.
there. What do you recommend? That's fine. I mean, I guess Hot Springs be one of the areas. It's solid.
I heard the Hot Springs area has pretty good weather for that part of the country. Because again, weather, clouds, clouds are your worst enemy. Yeah. So hoping for clear skies. There's maps all over the internet right now. NASA, of course, has a good one. And You know, the path is usually about 100, 110 miles wide, and then they'll show that on the map. And then they'll show a blue line usually right in the middle. The closer you can get to that blue line, the longer totality will be.
For the live stream, would you mind repeating that question? And then I'll give you the mic, whoever's next. Could you just summarize that last question from the asker, if you wouldn't mind? Because I don't think the live stream heard it.
Yeah, he was asking about his location in Arkansas and sort of where's the best place to go. So again, clouds are your enemy if you're going to be in the path. So if you wake up and it's cloudy, you might want to drive. And then again, as you get to the center line, it gets longer. The edge of the path is a few seconds. The center line is around 4 minutes on this one.
So my question is probably dumb, because I know there are no dumb questions.
No dumb
except this
questions.
one. So I'm curious. We've been watching these eclipses now for a while. Have they changed over time?
Great question.
Oh, it's not a dumb question?
So no. So it brings to mind a bunch of things for me. So every eclipse is different based on like solar maximum, solar minimum. We were talking differently. Again, I've seen a bunch, and the corona is always very different. They're always in different parts of the world. And again, the celestial mechanics are complicated about how long they last. They can be, 7.5 minutes is about as long as they can be. There's a lot of eclipses that are 1 second in Antarctica. It all, the curve of the earth, the shadow on a curved ball, it's very confusing. But it is true that the moon is moving away from us. So in something like, I want to say 5 million, it's longer than that. 2 billion, way past our time. After the conference ends, past your lifetime, there will be a time where there will no longer be solar eclipses, total solar eclipses. No, wait, the moon's getting, I'm sorry, closer to us.
You're right.
Okay, somebody check my science. There will just be annular eclipses. But in our lifetime, generally speaking, there's a chance twice a year, and that has to do with the celestial mechanics, the way they're moving. Usually, on average, they happen every 18 months.
So I appreciate you talking about last week, because at work and using of technology, it was a sucky week because there were problems and it felt with maybe the solar flare thing. So my follow-up stupid question is, there's an awful lot of technology out there in space, right? With all these satellites. And we are becoming more and more dependent on technology. Is there a predictive analytics to when we're going to have problems other than Googling when is Mercury in retrograde?
Yes. So the active sun. So again, we were talking a lot about solar flares and CMEs and all that sort of stuff. And they do definitely affect our satellites in space. And I think he's going to show us what we've got going on out there. We're desperately trying to predict it. Right now, the scientists cannot predict when there's going to be these giant eruptions outside of, we know it's more active every 11 years based on a cycle. But sometimes it's 11 years, sometimes it's 13 years, sometimes it's 8 years, we don't know. So NOAA and NASA especially are working really hard to figure this out. And it does fry the electronics on satellites. And that's just becoming a bigger and bigger problem because, do you want to talk about that?
Oh, yeah. I was trying to, once again, we can't really see the magnetic field too well, but maybe I can. So what I'm showing here are geostationary satellites. So they're some of the highest altitude satellites. So this is probably the outer limits, but they are used a lot for weather satellites and things like that. And they're actually just inside Earth's magnetic field, but during an event, the magnetic field compresses even further, and those can be outside the magnetic field. And then the orbit of the moon is sort of encircling. So this is the orbit of Earth around the sun from the lower right to the middle. But the orbit of the moon is pretty much outside the magnetic field of Earth, and that's why it's dangerous for astronauts. If we talk about sending astronauts back to the moon, this is going to be something that we need to be cognizant of. So again, another reason to study these phenomena.
Yeah.
We are at time, so maybe just a closing.
Yeah, just
No,
one more,
yeah.
since we're at scenic, I think another, just one of the things, one of my colleagues at NASA is studying is some of these events can cause cosmic rays, and those are affecting the cloud. So all of the computers that are under freeways or, hidden away that we use as our cloud services, those are being affected, and solid state drives especially are affected by these events. And so this is something that's there was a great NPR article on this last year, because now, of course, we've got these kind of electronics in our cars as well. And so there's all this kind of redundancy that the engineers are having to create in order to keep these events from causing us a lot of trouble. And also why we want to predict them better.
This is
Do you wanna-
amazing. I love when it keeps going. This is good. I think we're gonna have to close the session out of respect for time for everybody. But round of applause, number one, for a live demo that works on Ryan's half. And so Robyn and Laura, thank you.